a donut around here and then call it a day. Hopefully I get more turning with the wheels. And hopefully I don't spin out. So here we go. Let me back up. Get the revs going a little bit. And just hit it. Like a dream. Alright, let me turn off the circuit.
Hey everyone, I just want to say thank you for all the recent support, whether it be just watching or subscribing. It really means a lot. Trying to play a song through the car horn was the whole reason why I got into microcontrollers. For everyone who's subscribed for the Minecraft builds, I plan on showcasing each build in one video and have it out by the 17th, since that'll mark 6 months from when I first started with the initial daylight sensor. While working on this video, I've also been working on piston doors, which will also be coming out pretty soon. So again, thank you, and I hope you enjoy the rest of this video. Here's a little circuit that I added. It's using an ATtiny85 microcontroller, and it's driving a MOSFET. Under the MOSFET is a resistor in order to pull the gate down to ground. Without the resistor, the gate is unable to drain, keeping the MOSFET powered. From the added circuit board, I have the red wire going to power directly onto this potentiometer. Potentiometer sets the threshold RPM. In order to send that information to the microcontroller, the potentiometer is used as a voltage divider. We have 5 volts here, divided voltage in the middle, and ground on the right side here. Along with ground, I have a thicker gauge wire here connected to the ground of the main PCB, connected directly to the MOSFET ground, along with the ground of the ATtiny85. Another thicker gauge wire is connected directly to the MOSFET, directly to the source, and so when the MOSFET powers on, it allows current to flow from the source into the drain down to ground. In order to get a signal from the main board, I'm using this yellow wire connected to the ATtiny85. It's directly connected to the LED so that when the LED turns on, the microcontroller can read the voltage and then run the code. When testing, I accidentally burnt down the original LED, so I just replaced it with a little 3mm LED. I was able to just screw in this PCB along with the original PCB here, allowing it to be pretty secure. See, it doesn't move around. Now looking through here, you can see a bunch of the connections. We have red connected just directly into power when the ignition is on. The white wire is for the lights to be turned on for the meter itself. So right now I don't have it hooked up, it's just there. The black wire is ground running over here down into a bolt, and finally the blue is running all the way down connected to a switch straight to the negative side of the horn. When the MOSFET gets powered on, it'll allow the current coming from the horn to run through that MOSFET and down to ground. When these lines are disconnected from one another, the MOSFET will still be powered by the microcontroller, but the current will no longer be able to flow from the horn and down to ground. The way the horn works in this truck is that it waits for a ground potential. So looking at the horn itself, it has a positive 12 volts. On the other side, it has a line running all the way to the steering wheel. So if I open up the horn, you can see there's a wire, and it just connects up to this plate. Now when I press down, this metal plate hits this metal plate here and is connected to ground.
Alright, let's go test it out. I have it all hooked up. Everything's running pretty good. So now if I want to do another one, just a short one, need another diode just to help. When I get home, I'll just try it again while I'm just standing still and see what happens. Give it a try. Yeah, it's done. Gotta be something in here that messed up. Let's crack this open. So the MOSFET is not hot at all, and neither is AT Tiny. So what I'm gonna do is add another diode. Alright, so I added the second diode. You can see that the horn still works. So now let's turn it on. Let's try it again. And it also sounds a little louder. So it's definitely the Schottky diodes that are allowing the voltage to go back into the horn, reducing the voltage spikes that it sends back to the MOSFET. I'm gonna drop the gear, see what happens.
There's one issue that I still don't understand quite well. When I was using this circuit alone, without any diodes connecting the horn negative to the positive end of the horn, often the MOSFET would continuously have stayed on. Also, it would affect the timing of the AT Tiny. So you can see here in this clip. Now if I slow down this clip and play it, you can hear that the song is still being played. A reason for this might just be noise coming from the ground affecting the AT Tiny 85. When I first started, I was using the Uno board here, powered by a 9-volt battery in order to power the relay here, which I don't recommend since there's a possibility of burning out one of the pins here. If you have a relay module, those are different. They have an onboard MOSFET along with some diodes and resistors in order to protect the pin. When I was using the board and the relay itself, without any diodes on the horn itself, I didn't find any problems. But as soon as I moved to using the same power source through these linear regulators, and even using these buck converters, I started having problems where the microcontroller would either keep resetting or the microcontroller would have timing issues or continuously power the MOSFET. An inductor is a coil of wire that's wrapped around a ferrous material. When current begins to flow through the wire, a magnetic field is created inside this ferrous material here. If current is cut from flowing through, the magnetic field that was once created will soon collapse, and this collapse will induce a new voltage in order to try and sustain the magnetic field. This wouldn't be a problem if you were only cutting off the input voltage, since current within the inductor will still be able to drain into the ground, meaning that this new induced voltage created by the collapsing of the magnetic field will still be able to flow down to ground until the whole magnetic field has completely collapsed. The problem with disconnecting the ground is when the magnetic field collapses, there will be a voltage buildup since there's nowhere for current to flow, creating a more positive on the negative terminal side than on the positive terminal side, making the current flow backwards through the inductor until the magnetic field completely collapses. In order to avoid the buildup of voltage, a diode is used in order to connect the negative terminal side to the positive terminal side. This means that current cannot flow straight to the negative since this diode serves as a check valve for current. Instead, the current will be able to flow through this diode and around the inductor until the magnetic field completely dissipates. When the induced voltage dissipates, both sides will return back to normal. The diode will continue to serve as a check valve, while voltage will stay consistent throughout the inductor. Despite there being voltage within this inductor, since the ground is cut off, and also since this left side has the same voltage potential as the right side of the diode, current will not flow through the circuit until it gets a connection to ground, or it will rebuild its magnetic field. The horn uses a coil in order to move a plate back and forth, creating sound waves to be emitted. Diodes are used to connect the negative end to the positive end, allowing current to flow through the horn despite it no longer being connected to ground. When diodes are used in this configuration, they're referred to as flyback diodes. Right now, since there's 12 volts in the left side and 12 volts on the right side, no current flows. So here's a circuit I used in the memes on a car horn. Again, it's using the AT1085. That's just switching on this MOSFET on or off. Right here I have a button that can be used as a signal. In this design, it's using one of the pins as a pull-up resistor, which means that when it's connected down to ground, it'll be able to detect. You have a line that connects to the steering wheel, and so when the steering wheel is pressed and it's connected to ground, it'll be able to also detect that. I had two versions on the code. One version would determine how long the horn was being pressed for. And so it would play a different song depending on that. The code used for the video was just toggling between each different song. So every time I would press the button, or I would press the button on the steering wheel, it would advance to a different song. In order to power the AT-Tiny, I used a different circuit here. It's using a linear voltage regulator here, along with some capacitors in order to filter the voltage. Here I have the same circuit, but instead of just using the MOSFET in order to allow current to flow through, I'm using a relay. The relay itself is an inductor just like the horn, which means that it's recommended to also use a flyback diode, as you can see here. Since relays draw a lot of current, a MOSFET is needed in order to communicate the microcontroller between the relay. The MOSFET will be powered by voltage alone, so no current will be drawn from the AT-Tiny pin. The MOSFET will then allow as much current needed to flow through this relay here in order to power it. Again, a linear voltage regulator is used here, along with some capacitors.
A ver. Oh. ¿Qué marca hay?
Los revoluciones.
Oh, las revoluciones del motor.
Sí.
Te quedó más suave así que el monito, que el mariachi ahí.
Nomás que no tengo para pegarlo. Tengo que comprar.
¿Y si no le puedes meter un screw así?
Sí, pero no quiero
girarlo. ¿Con silicón?
Tampoco. Nomás voy a comprar un tape.
¿Un tape negro?
No, un tape.
De ese que. Ajá. Así nomás. Mira, está curioso.